Okay, welcome to this video, and we are talking about issues and acceleration in terms of root finding, and this is based off of what we did in the last video, the fixed point method, which that led us directly to Newton. So we're going to talk about issues, and I think I spelled this wrong. Multiplicities. There we go. All right, so what happened in your last homework? What happened? So I think you should have had the experience that something didn't work quite right. Newton did not outright fail, but there was something that went wrong, and I will let you figure that out. But what would cause that to happen, right? So we want g of p equals p. So we want a fixed point p such that g of p equals p, and remember that happens when f is 0. So we are trying to design g of x to be like x minus f of x times some other function, and remember for Newton that phi is the reciprocal of f prime. Okay, so we know that whatever happens, this phi has to cause this component to be small-ish, and it has to respond to f prime so that the sign matches appropriately, because we want to make sure the derivative is just under 1 or over -1, but we want to make sure we don't go on the other side. We saw that bad things happen even if this g prime is 1.1, bad things happen. Okay, so we want g prime of p is equal to what when f of p equals 0. So it's going to be just 1 if f prime of p ends up being 0, right? So we need this kind of thing to happen, or actually we need g prime to be 0. Let's see if this works. What happens? Let's see what happens. G prime, is it 0 or 1? G prime of x is going to be 1 minus, okay, first times the derivative of the second, and then the second times the derivative of the first. Okay, so let's see what happens. So if we know that we know that f at p is equal to 0. So if we're going to evaluate this at p, then this term is going to turn into a 0. Okay? What if we want f prime of p to be 0? Let me just clarify that a little bit. So what's this deal? We said already that we required g prime to be less than 1. So we allow this kind of situation. Here's g prime, can go between -1 and 1. But we already found out that because of our experimenting with Newton's method and dividing by f prime, the closer to 0 the better. Okay? So the thing is, it's okay if you stray from 0, and as long as you don't go above 1 or below -1. But if our goal is to make this as small as possible, we're going to have the best convergence. If you remember what our fixed point method looked like, you know, when we had this very, very flat curve, we had the best convergence at the fixed point. So even though it can stray, we want to see if we can get it as close as possible. If you remember, again, those cobweb diagrams, everything's just going to zoom in faster when you have a very flat function here. So that's sort of the deal. So it's okay if it's not perfectly equal to 0, but it's going to be fairly close to 0, so we can at least put that on our wish list. Okay, so our wish list is for g prime of p is to be about 0. Okay. Now, what happens if it's exactly 0? Let's just let it be 0. What we end up with is this situation. So we end up with, let's solve for that. F prime phi is equal to 1, or phi is equal to 1 over f prime, which is what we got for Newton. This was our Newton's method. So if this is generic, you could express a fixed point method this way, and if you let phi equal to 1 over f prime, you're going to get Newton's method, and you're going to get g prime of p being close to 0 by that mechanism. Okay, now this is completely awesome when it works. Okay, why am I having so much trouble controlling my screen? I hate this. Ugh. Okay, I adjusted it slightly. Maybe I'll have control of it now. Okay, anyway, this is awesome when it works. Awesome when it works. But it doesn't always work. And that was something you discovered in your homework. What happens, for example, what if, this isn't exactly what happened in the homework, but it was close to this. What if f prime is equal to 0, not just f of p equals 0, but f prime is also 0. There. Now, if that happens, what happens? Horrible things will happen. Ah! Okay, so what we've run across is zeros of multiplicity higher than 1. So for example, we talked about x squared, x cubed, x to the fourth, and we know what happens, so we can plot those or whatever, and we can look at x squared, x cubed, x to the fourth, x to the fifth, things like that. And if we have multiplicities on our zeros that we're trying to find, then we're going to jam up in Newton's method. Okay, so can we get rid of this problem somehow? Can we just like divide away this problem? And the answer is, of course, or I wouldn't be suggesting this. Okay, so let me just think about this way. Okay, keep losing my eraser here. There we go. There's my axis. And I'm going to give myself some kind of a function with a multiplicity, 0 multiplicity. This is essentially y equals 1 plus sine of x, but I just did a bad job drawing it. But that function, for example, has a root here, a double root at 3 pi over 2. It's something you should know. So what if we could say instead y2 is equal to 1 plus sine of x, and okay, this is what we do as academics. We pretend we know the answer to the problem we're trying to solve in order to get a better technique for solving it, which is really stupid. It's kind of like using pi in your calculation of pi, which is just dumb. But just bear with me, because we're gonna get to a point where this is helpful. But initially, this is an academic exercise to say, what if we could just get rid of this root? Okay? All right. So if we put a square here, we should get rid of this root. If we put a 1 here, we should reduce that root to order 1. And if we put something like a 3 here, we should get an asymptote. So let me pause for a second to pull up Wolfram alpha so we can do some plotting here. Okay, so I just plotted 1 plus sine of x, and you can see the double root is where we expected it to be. But now, what if we want to try to divide out by some bit of that? And I'm going to say x minus 3 pi over 2, and see if Wolfram knows what I'm trying to do. See if it can handle that I spelled pi with a capital and a lowercase p. Apparently it can. So look what happened. Since we happened to know where the root was, we were able to divide out, and now we got a single regular old boring root. Well, what if we squared that? Can we get rid of the root altogether? Now we're thinking in terms of L'Hopital's rule, like big time. So we actually completely got rid of the root. Now it's not a 0 at all. But what happens if we crank this up even further? We're going to end up doing something really stupid. Oh, it's not stupid. We're doing it on purpose. We actually created an asymptote where we used to have a root. So this is kind of weird. Okay, so what if we divide by -1? Can we like crank up the value of that root? Oh, of course we can, because then we're just sticking it in the numerator. So now it's an order 3 root. So this notion that we can just kind of like divide away the root and get rid of it is kind of cool. Like we don't want to get rid of it. This is this idea of a removable discontinuity. We just removed it. But if we want to just get rid of one copy, let me go back. This is just kind of mesmerizing. So if you've never done this kind of thing before, you should just go ahead and do that and enjoy that little exercise. So this will get rid of our root. This kills the root entirely. Okay? So yes, you should get this L'Hopital rule feeling. So now we want to get some kind of definition going. What is the formal definition of a duplicate root? Okay, here's our definition. A solution, so if you have a 0 in f at point P, okay, solution of P, it's a 0 of multiplicity m of f. We're talking about f still, not anything else. If for all the points that aren't P, so we're talking here removable discontinuity. So you should be thinking removable. This is what we mean by removable. For everything else, we can write f of x is some q, some quotient or some leftover piece of the function, okay? And then we've essentially allowed us to factor out x minus p to that power m. So we're actually factoring out that duplicate root, and we're saying if we can get rid of that 0 so long as it is essentially a removable 0 in the same way you would have a removable discontinuity. It's exactly the same thing, but you're doing it in the numerator instead of the denominator, okay? And the point is that q of x is not allowed to be 0 because that would mean there are more zeros to remove. So the point of this is saying when you say 0 of multiplicity m, it means you got them all. I can't say this is a 0 of multiplicity 4 and then make the claim it's 0 of multiplicity 6. So the language you'd use instead is you could say this is a 0 of multiplicity 4 or greater, that's fine. But when you say 0 of multiplicity whatever, you mean you've nailed it exactly, and that is the total number of zeros at that point. Okay? So there's that definition for you. And q is the function of f with all those zeros having been washed out at that point. All the rest of the zeros are totally fine. We've just washed out the zeros at that point. Okay? When m equals 1, we call that a simple 0. Similarly, if you can have the concept of a simple pole. Like if you have something like this, you have a simple pole or a simple asymptote, right? So if it's in the numerator, we would call that a simple 0. Okay, let's do a fun example. Okay, let's recall. F of x is, let it be e to the x, and then we have our Maclaurin expansion, okay? What's fun about this is you can easily create, this is a very common pedagogical trick that the instructors use and textbook authors use. We know that g of x is definitely 0 where, well, so e to the 0 is 1 minus 1 plus 0. So like you've obviously zeroed it out. This is kind of like e to the x minus e to the x, and it causes you to get these duplicate roots. So you can make this duplicate root as deep as you want by just taking the actual function and subtracting out your Taylor expansion. You can just add another term to that if you like, but I don't want to add more terms. So I just want to keep it kind of simple for this example. But if you see that example, you see something that suspiciously looks like a function minus part of its Maclaurin expansion, that's a textbook exercise. That's not a useful function somebody got out of industry. That's a textbook example. Okay, so we're going to use this Taylor subtract trick and to get zeros of any multiplicity we want. Okay, so I'm going to now do this exercise. I'm going to say g of x, so pretend like you didn't hear that teacher trick. Okay, e to the x minus 1 minus x, and I hand off this function to my students, and then they calculate, okay, g of 0 equals 0, and we want to we want to patch over the 0 and see if we can build a q in this situation. Let's see, g prime is going to be e to the x minus 1, g double prime of x is e to the x. Let's just do this. G0 equals 0, and this is going to be multiplicity 2, but we're just going to keep going until we get a 1. So we have a root here of multiplicity equal 2 because we got 2 levels of zeros, okay? So we have constructed in this way, we construct and verify, we made and verified G has a root of multiplicity equal to 2 at 0. Okay? Now we can patch over the 0 by dividing back out. It seems like circular reasoning, like we just created a 0, but the point is maybe we had a function out in the wild that had similar properties to this fabricated function. So e to the x minus 1 minus x. If we do this, we just reduced this to multiplicity 1. And if we want to completely get rid of it, let's just give this another name, e to the x minus 1 minus x. This time we're going to divide by x squared, and now the root should be gone, or the 0 should be gone. So let's just see if we can pull that up on Wolfram Alpha. Hopefully I've still got that web page up, and let's see if we can do that. Plot e to the x minus 1 minus x. Where did you go, Wolfram? Come on, there we go. So I want to do e to the x, e to the power of x. We're not in Python, so we can use that exponent key. Okay, and then I'm just going to get rid of this for now. I'm just going to 1 to the power of 1 and just look at this thing. Maybe it's not such a good domain. We'll find out pretty soon. It's probably okay, right? I don't know, where is the 0? Let's make it just go to pi. Can we find the 0 here? Can't even see it. Where is it? It's at 0, so actually we probably want to go something like minus 0.5 to 0.5. Oh, that's much better. That's what I was looking for. Okay, now if I want to divide out, I can divide out by x to get this to be a normal root, because we know it has multiplicity 2, and if we wanted to get rid of it altogether, we're going to also show what happens when, well, I have no idea why it's taking so long. Okay, and if we want to just make it multiplicity 0, like we can get rid of the root altogether, just divide by x squared, and then there's going to be no 0, and then we are back to the L'Hopital type situation where you want to get rid of the root altogether, and so you essentially divide out by the full amount of the root. But we actually wanted to find the root, so let's go back to just divide by x, because this is the situation we really wanted. And so what we're going to do is we're going to develop a numerical technique that essentially simulates what we just did by hand. We're going to try to divide out by that root. But we still have a problem because we don't know where that root is. This is kind of the circular reasoning. If we don't know where the root is, how are we supposed to divide out by it? Luckily, we have a trick. What do you think the trick is? Well, the whole point of this, the whole reason we're having trouble in the first place, is that the function and the derivative have roots in the same place, and this is what's causing us trouble. So what about we just let the derivative itself find that duplicate root for us? When you take a derivative, one of the things that you expect to happen is that the root that was a triple root became a double root, or the root that was a double root became a single root. So by dividing out by the derivative, you do actually locate the root and divide out by the correct number of multiplicities. What a cool hack. Hey, that's pretty neat. Okay, so now let's do the following. Newton's usually looks like this. Okay, Newton says that you're going to say your starting value is whatever it is, and then the iterative step looks like this. What we're going to do is we're going to take this piece and we're going to call it mu of x, and we're going to actually run Newton's method on mu of x. Okay, we're going to adjust Newton's method. And so when I say in your homework Newton-Raphson, this is the one I'm talking about. So I'm just thinking of this as adjusted Newton. If mu is f over f prime, and we want to have the new method be xn plus 1 is going to be xn, so let's just call this adjusted Newton. Okay, we're going to do minus mu over mu prime. So we need to work this out, and this is going to be something I'm going to do for you, but I want you to do it first. I want you to do the following. First of all, how do you take the derivative of mu? So mu prime is, I'm going to just write this symbolically. I'm going to pause the video and ask you, you are going to pause the video, I'm going to ask you to figure that out symbolically. Okay? All right, hopefully you did that, and I'm going to pause again in a second, but right now I just want to figure out the derivative of this mess. Okay, so it's going to be the bottom squared. I'm just going to write it this way, and then the quotient rule says the bottom times the derivative of the top minus the top times the derivative of the bottom. Okay. All right, so now the next piece I want you to do, I'm going to ask you to pause again. I want you to calculate mu over mu prime. So here you have mu, and here you have mu prime, and I want you to do out all that messy stuff and then simplify it as much as possible so that it looks kind of cool. And then come back and see if you agree with what I get. Okay, hopefully that you did that. And so if I take mu on top, which is f over f prime, and then I want to divide by mu prime, I'm just going to invert and multiply this, right? F prime squared. And so then I get f prime squared in the denominator minus f double prime. Technically you're done, but that's super sloppy. So we're going to do some algebra, right? You're going to cancel out one of these guys, and that's at least the first step. Then you get f times f prime, and then in the denominator you get f prime squared minus f double prime. All right, and so this is how you get your adjusted Newton. So adjusted Newton just comes directly from that. Hopefully you agreed with that. So we're going to just rewrite this nicely. Okay, so your adjusted or your upgraded Newton method, which you're going to be using in this upcoming homework, it's going to look like this. It's just really Newton, but you're just feeding it in a new function, which is f over f prime, and then it's Newtons from there. But in terms of coding, you're going to have to, have three separate functions, f prime, and f double prime. So what's going to happen is with all these homeworks, you take the derivative by hand, or maybe you check it out on Wolfram Alpha to remind yourself how to take a derivative, and then you essentially implement those derivatives in your code. So at this point, we're not expecting your code to be taking any derivatives. Okay, so we just fixed Newton to improve what's called the convergence in cases of higher order zeros. What does that mean? Well, we actually took something which is known as linear convergence, and we turned it into what's called quadratic convergence. And I want to talk to you about that, because it may not be what you think. Linear isn't linear per se. Okay, so if we have a sequence, we're just calling it P sub n, and it converges to P, if the following holds true, if we're taking the limit of the error of the n plus first term, divide by the error of the nth term, for first of all, just pretend that alpha is 1. So if that ratio is essentially constant, then we call this convergence order alpha. Now in real life, they're not going to be exactly identical. That would make no sense. If it were exactly identical, we could get it in one step. But the point is, it's essentially the limiting behavior is it's close to a constant, then we call this linear. And if you can actually square the error on the bottom, remember these are small errors, so when you square them they get smaller. So it's not like you're taking 4 and squaring it and get 16. It's like a half, and you square it and you get a quarter. Okay, so if those are roughly the same size, then you would call that quadratic convergence. Okay, so let me just sort of show you what I'm thinking of when I see that. Okay, I'm thinking of, here is my ultimate goal over here of like P, and if I have like, here's my starting value for P, what would happen in a bisection situation? Bisection is an example of linear. This would be roughly where you expect the P1 to land, and then P2 is here. And this is why I'm saying it's not really linear per se. I don't know why they call it linear, but when it converges like this and the error keeps going down by half, 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 if you graphed the error, it would just look like this. So that's not a line, right? That's just like 1 over x or something like that. You know, this is like, or 2 to the, you know, it's 2 to the minus x or something. So why do they call it linear? Well, if you graph it on a log scale, it would be linear, right? So one way to think of it is you're getting the same number of zeros or bits each time. So if I have something which after 10 iterations I have, you know, this much accuracy, and then after 10 more iterations I have this much accuracy, and after 10 more iterations I have that much accuracy, and after 10 more iterations, think of it as linear in terms of counting digits, not linear in terms of the actual amount of error. If you think about that, see, I just feel like you should be appreciative that the bisection method is actually quite powerful and actually quite useful. It's not that slow in the grand scheme of things, but it is slow compared to quadratic convergence, which is much, much more rapid. So quadratic convergence would be something like this. Like you do one, you know, like 10 iterations and you get this much accuracy. But 20 iterations and you get, you know, twice as many digits, and then 10 more and you're going to get like more accuracy. So it means that your accuracy is increasing with each step, not just the number of digits. I mean, your accuracy is always increasing, but the number of digits you get is accelerating in a sense, not just getting the same number of digits after the same number of steps. Okay, so that's what I want you to be thinking of in your head in terms of the difference between quadratic and linear. And you may say, what if I want to converge faster than quadratic? Well, go ahead, have fun with that. You're lucky if you have linear convergence and you can accelerate it to quadratic. That's pretty much what we're doing in this course. We're pretty much assuming that you're starting off with a reasonable method that has some kind of linear convergence, and that you're going to be able to squeeze a little more out of it by turning it into quadratic convergence. Okay, I need to like set up for the next section. There we go. Okay, so let's say we don't have quadratic convergence. We're kind of lucky because maybe we already have linear convergence and we just want to speed that up. So what that means, according to our definition, is this formula here is true. What does that mean? So I just wanted to give you a visual. We just talked about that, but I think it's just worth repeating again. If my distance from, okay, here's my original starting distance, okay, and I tried to make it like we're coming a third of the way in. So each iteration I'm coming a third of the way in. So the ratio from here to here should be like 0.67, something like that. Okay, so if that matches like all these successive iterations, so for example, the distance between P0 and P2 versus the distance between P0 and P and P2 versus P and P3, that ratio is about 0.67 as well. So I keep coming in at the same relative rate. If that holds true, then what I have is linear convergence. Now, what that means is now, if this were perfectly true, it's not perfectly true, but if it's close to being true, I should be able to, obviously, solve for what? Solve for P, obviously, because that's what we're looking for. So I'm going to pause for a second, or you're going to pause, and try to solve for P, and then we'll come together and see if we agree on that. Okay, hopefully you spent some time doing that. I'm going to try to solve for P, so I'm going to do this cross-multiplying trick. I never tell introductory students the phrase cross-multiply. I hate that phrase, but you're mature enough to know what I'm doing. I'm clearing out the denominators by multiplying both fractions by both denominators. Okay, so then I'm going to expand this P times Pn plus 1, but I actually have 2 copies of that, so I need to sort of put a 2 here, plus P squared. And right now, at this point, I'm scared. But don't be afraid. Just keep plugging away. Don't worry, the messy stuff will come later. At this stage, we get off the hook really easy because the 2 P squareds completely go away. Now, if you had trouble solving for P before, I want you to pause here and finish it. Okay, so hopefully you got it there, and if not, I'm going to go ahead and finish that now. I'm going to look for all the P's. Here's a P, here's a P, here's a P. And I'm going to put them all over to one side. P times minus 2 P and plus 1. I'm going to grab this one from the other side and grab the other one from the other side. And then anything that doesn't have a P in it is going to get chucked over to the other side. So minus P and plus 1. And then I have plus P and plus 2. And luckily that P squared disappeared. I'm going to then double check everything. I'm going to pause for a second to make sure I didn't make any mistakes. Well, of course I made a mistake. I'm recording. Crazy me. So what happened when I FOILed? I forgot to square my F term. So that's why this guy forgot to get a squared over here. So that's supposed to have a squared. Okay, other than that, we're good to go. Alright, so P is just equal to, or it's approximately equal to, we're going to put this guy on top, and in the denominator, let's just rearrange this so it looks a little nicer. And I think that's fair enough. What do you think? Okay, and you can switch those 2 terms on the top if you prefer. I don't really care. Okay, so to make a fixed point method, this isn't going to fly, is it? Because even though I really like this, how do we get from one step to another? This is going to be a mess, because first of all, we're going to have to start with Pn and Pn plus 1, which is fine. And then we're going to have to solve this thing. Actually, Pn plus 1, basically it's just going to be, a mess. So let's go ahead and do something else with this. So let's do some algebra on here. So what we want to do is we want to rewrite this. Okay, as odd as it sounds, we want to rewrite this so that it's identical, but we're going to essentially factor out a Pn, and then there's going to be a minus, and then there's going to be a whole bunch of garbage over here. Okay, so we want to rewrite this, so we need to literally factor an Pn out of that massive equation, which is it's a total pain, but I want you to do it. I'm going to pause and let you do that, and then I'll come back and I'll have the answer on there. So how are you doing on that? Did that work? If that didn't work, then here is a clue. I will continue working, but I just wanted to pause and give you this clue. Okay, so if you want one more clue, here it is. And now I'm going to continue the work. Okay, so I just took this thing and subtracted it from itself. Pn minus Pn, and then this is exactly the expression up above. And now I'm going to combine everything by distributing the Pn over into the numerator. Okay, and now we're going to start with some heavy-duty algebra. What can we do with this mess? Okay, so this Pn plus 1, or Pn plus 2, we have okay, found my error. What happened is when I joined these two fractions, I forgot to join the plus with a minus minus. So this should be minus a negative, so I should have distributed this negative. This needs to be a plus, and this guy needs to be a minus. So algebra, okay, so this piece is going to cancel with this piece, which it's supposed to do. Okay, now what's crazy now is this numerator is going to factor, right? So we have this piece and these guys together. These guys are going to factor, so it's going to be Pn plus 1 minus Pn, and it's going to square. Alright, so that actually all this mess is going to start looking nicer. So your method is going to look like this. Pn, so P is approximately, so this is how you're going to get your next iteration. It's going to be Pn minus 2Pn minus 1, which we're going to give you something else pretty soon. I'm just making a mess out of this screen. Okay, Pn plus 2. And now the numerator is Pn plus 1 minus Pn squared, which is lovely. Okay? And so we're going to call this P hat sub n and get rid of the approximately equals, because that means something. That means you already have a sequence that converges linearly, and what we're going to do is we're going to define P hat to be this quantity. Okay, so P hat is a better approximation to P than what we had before. It's saying if you already have a Pn plus 1, this is supposed to be a plus, not a minus, sorry, Pn plus 1 and Pn plus 2. Now we're actually going to give a word for this. This is called Aitken, and it's called the del square method. Okay, and if we were planning to stop here, I would not add more notation. This is quite enough. I don't need more notation for Aitken, but we're going to build on it when we go to Steffensen. So I have to add something at this point. So the point is, we're going to create a new way of writing this. P hat, so Aitken's del squared method, is going to be written like this. We're going to think in terms of differentials, and we're going to say this top thing is called del of Pn, and in the bottom we're going to write del of Pn squared, and I'm going to tear that apart in a second, but that's going to be equivalent, a different way of saying the same thing, different way to say it. Okay, you can probably figure out already del of Pn is going to be P of n plus 1 minus P of n. So you're thinking that's just like the numerator of the derivative. So it's the reason why we're not worrying about the denominators of these derivatives is because of the way we're dividing this out. All those extra little h's are going to just go away. So we're just going to ignore them entirely. Okay, so that it doesn't matter. We're really looking at the numerator of a derivative here. Okay, so here we are. And what does it mean del squared? Instead of actually squaring a del, what we're doing is we're saying if we want to square a del, we're actually saying del, we're saying my pen stopped working. This isn't good. I don't know how to get my pen back when it fails, so this is really kind of nasty for me. My computer stopped working too. Actually, everything stopped working. This is very sad to me. Please come back to me, computer. It's not working. Computer, please. Hello? Oh, yay. Good, 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 good. I'm so happy. Okay, so, what's happening if you want to do a del on a del on a del of Pn, what would that mean? So that would mean that the Pn itself is Pn plus 1 minus Pn, right? But then how would you del that? So you would do something like, it kind of looks like a second derivative. Okay, so this is the way they're going to end up defining it. Okay, so it's going to be Pn plus 2 minus 2 Pn plus 1, which is what we have in that expression up above. Is going to be Pn plus 2 minus Pn plus 1. And then from that, I'm going to subtract something. Pn plus 1 minus Pn. Okay? That's what, and so we're just going to regroup that, and then this is going to be del of Pn plus 1, and this is del of Pn. Okay? And that whole thing together we're going to call del squared of Pn. So you're taking the difference of the difference, okay? And again, we're forgetting all the denominators. We don't care about any of the denominators because all this stuff works out. Like the numerator and the denominator have the same degree and everything, so they all wash out. So we're really, as long as all the step sizes are essentially the same, which they're not, I mean, but it all works out. It's all kind of magical that way. Okay, so generically, we want higher order dels, and we're going to just say how a higher order del is defined. It's going to be del k of Pn is going to apply a del, which is just, you know, a numerical derivative or differential, to the previous level, and that's exactly what we did when we went from del to del squared. Okay, so that's just a more generic definition. Okay, so we've now rewritten Aitken's method like this. We're saying p hat, so we're starting with some other sequence and we're building Aitken off an existing sequence. So what you're imagining is a whole sequence that's we've already finished computing as much as we care to compute, and we're going to try to accelerate based on assuming it was going somewhere. We're going to try to guess where it was trying to go. Okay, so let's think about what this means. Okay, so we start with an originally linearly convergent sequence P0, P1, P2, P3, P4, and so on. And what I'm going to do, so this was some other method, not Aitken, but Aitken builds off of an existing method, right? So what you're doing is you're taking this group of 3 and you're renaming it P0 hat. And then I'm just going to change color because it's kind of hard to see what's going on here. We're going to take the next 3 and call that P1 hat. And then we're going to take the next one and we're going to go from 2, 3, 4, and we're going to call that P2 hat, and so on and so forth. Okay? So you're just going to keep shifting it. Just keep shifting it and build the next level of Aitken. And the idea is that the P hats, are going to converge faster. Okay? And so you're going to get, let's say if I say in the homework, start with 10, you know, P0 through P9. So you have 10 original items that are converging to P, if there's 10 of the original, there's only going to be 8 of Aitkens because you need 2 to get it started. So there's always 2 fewer of the Aitkens than there are of the original one. Okay? So now Steffensen, so this is Aitken. But Steffensen said, wait a second, you're wasting your effort. So we're going to just back up a little bit. Steffensen said, okay, we're going to start with just that red stuff. Okay, so this part is the same for Steffensen. So far, Steffensen's, but we're going to rename this thing again because Steffensen doesn't like this. We're going to rename this thing we just calculated in Aitkens. We're going to call it P1 sub 0, and we're going to say that that is del squared of P naught original. Okay, so that's the notation. All right, and then what we're going to do is, so in our original convergence, okay, let's just, now we need to say what was going on here. There was a G that took us here. So P3 is just G of P2, and so on and so forth. So that's how we were creating it on some kind of fixed point iteration method. Okay, so what Steffensen is saying is, why don't we go back to that original G, and we're going to take this guy and we're going to chuck it back into G, and we're going to call this P11. And then I'm going to take this guy and chuck it back into G again, G of P11, and I'm going to bring that out and call that P12. Okay? Now, that should be fine, but now what am I going to do with that? I'm going to say P20 is equal to P10 minus, and then we're going to use this thing we've been using. I'm not going to write it with a del because I think it'll be easier for you to code this up if I just do not use the del on you. Okay, so it's going to look kind of like this. Well, yeah, if I can get my stupid computer to cooperate. So P2P11 plus P10, right? So that's what you're going to get. And then he said, okay, now we're going to create P12 again using G. So we're going to go back to using G again to get the next 2 iterations. So Steffensen says, don't ignore how you created your sequence in the first place. Just hop on the train, and now we've got our second level. And all we need is 3 of them, and then we let the whole thing go again. So Steffensen's building out kind of horizontally, and whereas Aitken's kind of building vertically. Okay, so we're going to call this Steffensen. Actually, Steffensen probably called it Steffensen. I don't know. Somebody who likes Steffensen's method. Okay, so when you go to code this up, you're gonna base this off of this structure. Hopefully that is legible. I'm looking at that. I think it's legible. So this thing up here should be familiar to you now because we've been playing with it. It's the same as what we were doing up above, and we've listed it several different ways. Okay, and so hopefully that is enough to get you through, and that's the end of this video. And do ask me if you have any questions.